Hello, everyone. Thanks for coming. My name is Bob Steagall, and this is the second part of my talk entitled Adventures in SIMD Thinking. In the first part of the talk, I covered some primitives that we built around the Intel's AVX 512 intrinsics, some simple functions for manipulating data in registers. And then we looked at a couple of interesting problems, how to do intra-register sorting of values in an AVX 512 register. And we looked at how we could apply that to creating a fast linear median of 7 filter. I promised to look at 4 problems, then the other 2 problems are fast small kernel convolution, the first thing we'll look at. And the second is I will revisit a little bit of the talk I did 2 years ago at CppCon related to fast conversion from UTF-8 to UTF-32. In that talk, I did work using a DFA and SSE intrinsics to zero pad bytes to write them out more quickly. And I attempted to squeeze a little bit more performance out of that technique with some mixed results. So let's get started and move on to the fast small kernel convolution. So what is convolution? Well, convolution is a mathematical operation where a given signal, in this case f, is filtered by another signal g to create a different signal, usually marked f star g, and the star meaning convolution. So f is a signal and g is something that we typically call a kernel, and f star g is what we call the convolution. Every point of the result, and the point of convolution is that every point of the result f star g is f weighted by every point of g. It's useful for smoothing signals and for denoising. So let's look at a small example. In this case, I have a signal, a discrete signal, S, and it is represented by some sequence of samples, S naught, continuing. And for the sake of argument, and because there's limited space on the screen, let's assume that I have a small discrete convolution kernel that has 3 elements in it. I'll call the kernel K. It has elements K0, K1, and K2. I'm going to ignore the value of R1 at the moment because it's a boundary condition. I'm going to start for R1 because there are no boundary conditions that apply. So what is R1? R1 is equal to the signal at S0 times K0 plus a signal at S1 times K1 plus a signal at S2 times K2. In other words, it's S1 times K1 plus the corresponding product of its 2 nearest neighbors, left and right. And that's the value of R1. The 1 index here corresponds to the 1 column. And for R2, it's similar logic. The value for R2 is S2 times K1 because I've moved the convolution kernel over, S1 times K0, S3 times K2. And you follow this pattern, and effectively what you're doing is you are weighting in your result, for example, R2, the value of R2 is S2, S1, and S3 weighted by the convolution kernel. If this is a continuous infinite signal, it would be integrals and it would be a little bit messier looking, but for discrete convolution, it's pretty straightforward. And you can imagine implementing this as a nested loop, an outer loop that moves along the signal and an inner loop that does this computation for each value of the kernel at each point in the signal. So in this case, if we had n discrete points in our sample and we have 3 elements in our convolution, we can expect to do on the order of 3n multiplications and 3n additions, or 2n additions perhaps. So this process continues until you run out of discrete signal to be sampled. And here's another way of looking at it, a graphical way. Here we have our input signal. And again, I'm ignoring R0 because it's a boundary condition, and those are a little more complicated. And I've got my kernel, K, and I slide K along the signal. And for each stop along the way, I compute the product in the columns, add it all together, and that's what my result is for that corresponding element. So it's a sliding window computation. Well, we can rewrite the equations in a slightly different way. Remember before, I wrote them as though there was like a diagonal matrix, all right, almost. But let's rewrite them. Let's just stack all of the terms up along the left for R1, R2 through R5, and ignore R0 for now. Well, when I was trying to make this fast, it took me a while to come to the point where I figured out, what if I stacked them? What if I wrote the equations this way? Well, when I did it this way, I noticed something very interesting. I noticed that there was a limited number of columns, but one of the factors in each column was an element from the kernel. And I started looking at that thinking, well, wait a minute, I could put that in a register. I could put this in a register. I could put this in a register. Then if I was somehow able to multiply against these guys, I would be able to do this in a vectorized fashion. So thinking about it, I said, well, all right, let's think about it in terms of registers. Let's take this diagram and let's do a transpose. Let's transpose it around the major axis. So here we've got our signal, and we've got the values of the first convolution kernel element. And we've shifted the signal, and we've got the values of the second convolution kernel. And the same thing for the third kernel element. Well, if you look at what the value is supposed to be for R1, it is S0 times K0, S1 times K1, S2 times K2, that's R1. So if I could somehow contrive to load up some registers in this fashion, I could do this using my fused multiply and add function that I described in the previous talk. So in fact, that's what I did. And so I'd like to take a look at that function. Now, this is a function template, and it's parameterized in terms of the kernel size and the center of the kernel. And the center of the kernel basically is what point of the kernel do you want to call the middle? So because this has to fit into a register, the kernel size has to be 16 or less. It has to be greater than 1, and it has to be less than or equal to 16. And the index of the center of the kernel also has to be in that number range, greater than or equal to 0, and it has to be less than the kernel size. And because I was using median of 7 on my previous slides, and I'm somewhat lazy, in the examples I'm going to give you, I'm assuming that our convolution kernel has 7 elements in it. And later on, when you see the tests that I run, you'll see that I ran tests for 3, 5, 7, 9, 11, 13, and 15 elements in the convolution kernel. So we validate that our kernel size is correct. We validate that the kernel center is reasonable. And we compute the window center based on the kernel center. Now, convolution has this weird property where when you take the kernel signal in the kernel, before you apply it, you actually have to reverse it. And if you leave the orientation as it is originally, that's correlation. When you turn it the other way, it is convolution. If you have a kernel that's symmetric, then convolution and correlation will give you the same answer. So like before, with the median of 7, we have some work registers that use similar names to do similar things. We have registers prev, cur, and next, previous, current, and next registers, which represent the data input window of the data that we've read from memory. We have 2 work registers, low and high, where a lot of the dirty work gets done. And we have a register called sum, which is the accumulated value as you go through those sequence of fuse, multiply, adds. I have an array of registers equal to the kernel size that are going to hold the coefficients of my convolution kernel. So this can't be static, and it can't be const expert because my convolution kernel is provided at runtime. So this array and this loop are all runtime constructs. They can't be const expert. But what I am going to do is for each element in my array of registers that are going to hold convolution kernel elements, I'm going to broadcast the value of each kernel element into that array. So k coefficient 0 will have the broadcasted value of kernel 0, and so on and so forth. The next thing I'm going to do is I'm going to pull some data out of memory and load it into registers, my previous, current, and next registers. My previous register I'm going to load with zeros to handle the boundary condition. My current register I'm going to read from the beginning of my memory buffer where I want to perform the convolution. And my next register I'm going to read that from the next register's worth of data past the first read. So at the end of those functions, here are my 3 work registers. This is my zeros, this is my first register's worth of float values, and this is my second register worth of float values. Now I'm going to take my accumulator and I'm going to zero it because I'm going to reuse it, so I need to zero it before I begin the calculations. Next, I'm going to do this crazy operation I told you before, shift up with carry. And what shift up carry is going to do is it's going to take our work registers and it's going to load them with values taken from some combination of prev and cur. In effect, what we're going to do is we're going to treat prev and cur as if they were one large register that had 32 values in it. We're going to shift it up by the value that's the center of the window, and we're going to load the top of that register, those top 16 values, into low for this combination. We're going to do the same thing for high. So when we're done, we get a picture that looks like this. So we've taken prev and cur, we've shifted it to the right by 3 elements, which is half the kernel size, and we've loaded that into the low work register as I described. And the same thing for the high work register. We've taken cur and next, we've shifted them up by 3 elements, and we've loaded them directly down into the high register. And from this point forward, for the rest of the loop, we don't really touch prev and cur and next. We've got everything that we need to do our work now in low and high. So I'm going to take the prev, cur, and next register. I'm going to load them and with another value, and so they've all shifted to the left, and now we're going to ignore them for the rest of the loop. Now is when I actually do the interesting work that makes the convolution work. So what I'm going to do is for each coefficient in my kernel, which is stored in this array of coefficient registers, I'm going to do a fused multiply add of that coefficient stored in that register with the corresponding values in low, because low is going to be my primary work register. And I'm going to do the multiply, and I'm going to add what's in the accumulator, already in the accumulator. So I'm going to multiply the coefficient times low, I'm going to add it to sum, and then I'm going to store the result back in sum. So sum accumulates the result. So I have low and I have high. I have my coefficient 0, the first one that I'm doing. I'm doing a fused multiply and add of coefficient 0 and low. I add it to sum, and it goes into here. It's that easy. I go down and do another shift. This time, I'm going to take the combination of low and high, and I'm going to shift them to the left by 1. And that is effectively the same thing as taking that window that represents my kernel and shifting it upward by 1 or to the right by 1. So I shift it down by 1 and I do the fused multiply add operations again. And here's what that looks like. So now I've got coefficient number 1 loaded, and you can see that I've shifted downward low and high, and I've filled, because it's a shift, I filled the top end of high with a 0, which I represent by white. I do the fused multiply add. I multiply, I add, I accumulate in sum. And I will continue this a few more times for coefficient number 2, for coefficient number 3, for coefficient number 4, for coefficient number 5, coefficient number 6. And notice how the values in high have been shifting down into low, which is effectively the same thing as taking the coefficient register and shifting it upward. And every time I do this single step multiplication and add, I accumulate the result in sum. So because my kernel has 7 elements in it, and I've done the fuse, multiply, add with 7 coefficients, at the end of this loop, where I've done these 7 operations, sum now has the value of the convolution for every element that was originally part of Kerr. So when I'm done, I will store that out to memory, blast it out to memory. I'll loop back up to the top and do the whole thing again. And I've already done my shifting in the previous iteration of the loop. I've already shifted my data, a register's worth of data. I've already read that. So at the top of the loop, I'll actually do my shift up with carry and load for the next iteration, and then go through those operations again for the next register's worth of data. So I wrote some tests to test this because I wanted to compare it. I wanted to see how fast it was. And the benchmark I used was comparing it to Intel's math kernel library, which has its own very fast convolution algorithm in it as well. And people sort of think of that, at least in my world, as being, a good benchmark. They're sort of the, thought of as being the best performers there. So because I'm using AVX512 intrinsics, just like the median of 7 filter, I ran these on an AVX512 compatible system or capable system, which either Skylake or Cascade Lake systems are now capable of AVX512. This happened to be a Cascade Lake system. I built with GCC 10.2 and Clang 10.01. And again, as before, I compile with -03 and flags telling GCC and Clang, these are the intrinsics I would like you to consider emitting. I tested my results. I tested my algorithm against that of Intel's MKL 2020.1.217, which I obtained earlier in the year. I think there are probably 1 or 2 newer ones since then. And as I mentioned before, I compared my algorithm against Intel's convolution algorithm for kernel sizes, odd-numbered kernel sizes from 3 to 15, because remember, the kernel has to fit within a single register of 16 elements. This I did for element counts of 1,000 through 10 million, again, multiplying each kernel size by a factor of 10. And I collect timings for each combination using for each of those combinations. So there are 10 or so combinations of kernel. Well, let's see, there are seven, I think, combinations of kernel times 5 combinations of size. So I collected all the timings for those using the MKL-based convolution and my small kernel AVX-based convolution. And so here are some of the results that I got, starting with Clang. So kernel sizes 3, 5, 7, 9, 11, 13, and 15. And this is the factor speed up of the AVX-based approach relative to MKL. So for a very small kernel for any kernel size, for 1,000 elements, the AVX-based approach was significantly faster, and it was very fast for small kernel sizes. You can see for small kernel sizes and small amounts of data, it was significantly faster. The performance tended to converge as you got to more elements, and I expect probably a lot of the behavior that we're seeing here is elements being contained wholly inside of cache. And once we got to 1 million elements or more, we could no longer have everything in cache, and cache memory latency started to affect the calculations. And it started to affect the AVX calculations perhaps more than the MKL calculations. But in any event, even for a kernel size of 15 and for 10 million elements, and the performance here for kernel size of 15 was pretty flat. All across the board here, a kernel size of 15 was on the order of about 8 times faster than MKL. Well, I was pretty pleased with that. So this was Clang. For GCC, it was a little bit better, and I'm not sure. I mean, the MKL library comes as object code, so there's no changing that. That just gets linked into the program. So I can only explain this by thinking this was the same machine, same day, same hour running these things. I can only assume that in this particular instance, GCC is perhaps emitting more efficient machine instructions than Clang was. But in any event, there's more of a pronounced lean asymptotically with larger data sizes, but even so, everything tended to converge. For all kernel sizes, the performance tended to converge between 12 and 15 times faster at 10 million elements for the AVX approach versus the MKL approach. So I thought that that was some pretty reasonable results. In the code that I showed you, I actually did not include the code in the slides that accounts for the boundary conditions. But even with the boundary condition code, which is actually factored into these performance times that you see, you still get these results. So I was pretty pleased with that. I expect someone will come along and see what I've done and make it even faster, and I hope they do, and I hope they share it. Okay, so that's it for small element convolution, or small kernel convolution. Now I'd like to move on to revisit this topic that I've discussed before, UTF-8 to UTF-32 conversion algorithm. And I've included a fairly extensive portion, although not all of it, from the talk that I gave 2 years ago, because in order to describe the improvements that I made, I felt that it was necessary to include some context so that the improvements, I wasn't just showing you code that came out of nowhere, to provide some context for what you saw. So I want to briefly sort of walk through how the conversion works and look at the 4 different algorithms that I implemented: a basic algorithm, a simple ASCII optimized algorithm, an algorithm that's optimized for ASCII but uses SSE intrinsics, SSE2 intrinsics to be exact, and an algorithm that's optimized for ASCII that uses AVX2 intrinsics. So I'm going to jump into that. So without much ado and without really talking about Unicode, the way the algorithm works is it works by feeding a sequence of input bytes through a DFA. And the DFA is basically divided into character classes, which are represented by each of these ranges of octet. Remember, UTF-8 is at a minimum, or it is exactly, an 8-bit unsigned integer. So data comes in as a stream of octets, they call them. So there are 256 possible values, and these ranges correspond to state transitions that occur in the DFA when you encounter an octet that has a value that lies in that range. The transitions in the DFA that you see in this diagram are only for legal transitions. Any transition that causes an error or is an encounter of an illegal byte or an illegal transition goes to the error state. And there are too many arrows to draw that, so they are there implicitly. So how does this work? Well, first, let's take a brief glance at the basic algorithm, just to have some context. Basically, we get pointers to the beginning of the stream of octet, a pointer to the end of the stream of octet, and we get a pointer to char 32. And char 32 is what we use to represent the UTF-32 code points. So the stream of octets is called code units in UTF lingo, and the char 32 is the representation of the code points, which are the actual character values, if you will. That's not the right definition, but that's the best I can do at the moment without doing the rest of the presentation. So it's very basic algorithm. We scan from beginning to end, and we advance. And assuming that we don't get an error, we assign the code point that we get, that we return here, we assign the code point into a destination array. And we return the count of how many we decoded. So advance looks like this, and we'll actually step through it in a moment. But advance is the thing that actually works its way through the state transition table. And I have an example in a couple of slides. So let's assume that we're going to do an example, and we're going to decode this 3-octet sequence, E2, 88, and 85. So we're in the begin state, and we have our first octet, E2. So we look at all the outgoing transitions, and we see that E2 fits into these two character classes. It actually sits in this range. Okay, so we've read E2. So how do we do the transition? Well, we're going to advance. So we're calling advance, which means this is the beginning of an octet sequence. And without showing you the rest of the implementation, I'll ask you to trust me that there is a table for the first octet for any sequence that tells you exactly what the code point is. And so you look into the table, it tells you, it returns a value that has two elements in it. One is the first octet, and it tells you what the code point, the beginning code point is. And then it tells you what the next state in the transition is going to be. So the first state transition is special. The legal values of octets for the first octet in a sequence are different than the legal values for the second octet in a sequence, second, third, and fourth octets in a sequence. So in this particular case, we've got E2, and we are going to, because the first 3 bits are 1 followed by 0, we use the next set of bits to begin the code point. So those, we take that set of bits, we put them in the low order bits of code point, and we move on. And we're now at 8.8, by the way. We've advanced to 8.8. Okay, so we've gone through this state transition. We're now in continuation state 2. Our input byte, our look-ahead token, is 8.8. And lo and behold, 8.8 fits into the outgoing transition to continuation state 1. Well, we're still in advance. So we haven't encountered an error yet, and we still have input waiting. So we're going to create a temporary code point, which I've just assigned, which you just saw. I'm going to take that code point and I'm going to shift it upward by 16 bits. And then I'm sorry, the unit is the code unit that I just read. It's 8.8. So I'm going to take my existing code point, shift it up by 6 bits. I'm going to mask off the lower 6 bits of my code unit and mask them into my code point. Then I'm going to effectively use the next 2 tables, use the next table to look up the type of the octet, what is its character class, and given the character class and the current value, I can compute the state transition to the next state. So I've taken my original code point, I've shifted it up by 6 bits, I've taken the lower 6 bits of my continuation octet and masked them into the lower 6 bits of my code point. So I've moved into continuation state 1. My look-ahead token, the next octet, is 8.5. And I have a transition out of that that takes me back to the begin state, which is also the done state, the valid done state. So I do the same thing. I get a value. I extract the code unit from the array. I take my current code point, shift it up by 6, mask in the lower 6 bits from my code unit. I look up the character class, add it to the current value, and look that up in an array to tell me what the next state is. And this is the result of that arithmetic. I've now shifted my original 4 bits up by a total of 12. I've masked in the lower 6 bits from my first continuation byte, and I've masked in the lower 6 bits from my third continuation byte. And I'm back in the begin state, which is also the done state. So I return the value of the code point. And in this case, the code point is Unicode. They don't use hex, they use Unicode, 2205, which corresponds to the symbol for the empty set. I assign my code point into my destination array, and I go. So when I was developing this, I was looking at advance, and I looked at this and I realized, hey, this first set of operations I need to do, what if the first octet is ASCII? This is an awful lot of work to do if I have an ASCII octet to decode it through the table, to run through this branch, and then return if I already know it's ASCII. If it's already ASCII, why am I doing all this work? So I changed the algorithm to check if the current octet, the first octet in the sequence, is ASCII. If it is ASCII, I just go ahead and assign it from the source array into the destination array. And of course, this is 8-byte unsigned, and this is 32-byte unsigned. So there is an unsigned integer promotion going on here. But I bypassed all of those lookups and just simply done an assignment. I would have had to do a branch anyways in the previous implementation, but I didn't have to do any table lookup. So this branch that I'm doing here is not actually costing me anything, and I'm saving the lookups in those tables in the pointer arithmetic. Okay, so the reason I did that is I was looking at several source files from Wikipedia. I had this notion that I wanted to write a JSON parser, and to write a valid JSON parser, it has to everything that it takes in, it has to accept UTF-8, and it works in terms of UTF-32. And I thought, well, if I'm going to write a JSON parser, I better learn how to do this UTF-8 to UTF-32 computation. Okay, well, where can I get some things that have non-English characters in them? And the first thing that came to mind was Wikipedia. So I visited a bunch of Wikipedia pages, and I'll give you a list later, that describe various languages in those languages. And I thought, all right, this would be a good source for testing a UTF decoder. One of the things I noticed, however, when I was actually looking at the bytes in the file, was that even for languages like Korean or Japanese or Chinese, which have a lot of 3-byte sequences in them, or Eastern European languages that have a lot of 2-byte sequences in them, there were still large runs of ASCII character where you have a contiguous run of ASCII characters in the HTML code. And I thought, well, you know, maybe I could optimize that. And that led to the idea of the optimized ASCII algorithm you just saw. But realizing that there were so many opportunities for more optimization, I thought, well, maybe I can do better with SSE. So that's what the next section is about. So let's look at this case. This is the algorithm that I mentioned before, the improved ASCII algorithm. But can we do better? Well, let's assume that we're going to read data one chunk at a time. And for the sake of argument and for this algorithm, let's assume that we've got plenty of data in the destination array because we're not checking its bounds for now. Well, if I've determined that the first byte in this sequence at the top of the loop is an ASCII byte, there's a good chance there's more ASCII bytes that are coming after it. If so, why don't I try to convert those ASCII bytes using SSE intrinsics? So instead of just doing the direct assignment as before, I'm going to try to do some work with intrinsics. So I pass this inline function, a pointer to the current pointer to the source, and a pointer to the current destination. And so this is an overview of what that function looks like, and we'll go through it piece by piece. So let's assume that I have this, this input sequence, Greek word cosme. I'm told that's how that's pronounced. So when you take these Unicode UTF sequences, these code points that make this up, and you unpack them into a UTF-8 stream, this is what you get. So the first 11 characters here are all ASCII, so they all map to a single byte or a single octet. But these Greek characters most of them map to 2, but this character maps to a 3-byte sequence. So I've got 16 different code points, but they're actually mapped into 22 code units, 22 octets, or is it more? No, it's more than that. Okay, anyway, it's not a one-to-one mapping. So what we're going to do is see if we can snag these first 11 ASCII characters. And as I mentioned before, my convention is least significant byte or bit on the left and most significant byte or bit on the right. So here are some SSE registers, except these are 128 bits and not 512. I've got a couple of variables that I'm going to use to hold some data. One is a bit mask and one measures how far to increment, how far to advance the destination pointer. So the first thing I'm going to do is I have this 0 register, which I'm going to use for interleaving data. I'm going to fill that with zeros. Now I'm going to load 128 bits, 16 bytes, into this register that I call chunk. It's a chunk of data. So there, I've taken memory here, represented in gray. I've called the load intrinsic, and I've loaded it into my chunk register. Now I'm going to call this weird function called move mask to find which bits which octets in this register have their highest bit set. If the highest bit in an octet is set, it is not an ASCII bit. To be ASCII, it has to be less than 80. So when I call move mask, what it does is it looks and it says, all right, well, these first 11 values are all less than 80. They're ASCII. Whereas the next 5 values all have, the next 5 octets all have values that are greater than or equal to 80. So here I get a sequence of 11 zeros in my bit mask followed by 5 ones, indicating 11 ASCII octets and 5 non-ASCII octets. So this mask is important. We'll use it later. So what I do then is there are these instructions called unpack low and high to unpack 8 bytes or 8 bits into 16. So what I do is I'm taking the lower 8 bytes of my chunk register, I'm unpacking and interleaving it with values from the 0 register. And I call this half because I'm halfway there. So I've effectively 0 padded each of these ASCII bytes. So these are now 16 bits wide, or 2 bytes. The next thing I do is I do the same thing again. I unpack the lower half of what I had before, and I fill in, what it does is it fills in zeros in the second part of that. So here I'm taking the lower 4 units, these 4, and I'm unpacking these into 16-bit units and interleaving with zeros. So I get to quarter, I'm a quarter of the way done, and now I have 32-bit, unsigned 32-bit quantities that represent ASCII numbers that are correctly 0 padded. Then I'm going to write that out to data, pdest, so I write my first 4 code units. I'm going to go through the unpacking exercise again, except I'm going to start with the high 8 units of half, and I unpack them and interleave them with zeros, and I get the next 4 code points. And I'm going to write those out to memory. So I write those out to pdest plus 4. Then I go through the sequence again of unpacking the upper half of chunk. So here's the upper half of chunk. I'm unpacking high. I unpack and interleave zeros with that. I do it again to get the next 4 code units in the register quarter. I store those out to pdest plus 8. So now I've stored 12 code points in my destination array. I do the final unpacking from the upper half of the register I call half, unpack it into my quarter register, again, interleaving zeros to 0 extend the last 4 octets into 4 code units. I write that out, and now I've written 16 code units to memory. And this is an underlying assumption that there's enough memory to do this, that I'm not going past the end. All right, great. Well, I've written 16, but I know that only 11 of them are actually valid ASCII characters. How do I figure out how to do? How do I figure out how to adjust my destination pointer? Well, the next thing I do is I look at that mask that we calculated before. And if the mask was 0, that meant that no bits were set in the mask and all code units were ASCII, and I can just advance my source and destination pointers by 16 and move on. But in this case, the mask was not 0. The mask had some 1s in it. So we call another intrinsic, a function I wrap called getTrailingZeros, that calls different built-ins on different compilers. On Linux, and with Clang and GCC, it's built-in count trailing zeros, and on Windows, it's bit scan forward. But basically what these things do is they start at the lower bit and they count the number of zeros until they come to a 1. So in this case, it's going to count 11 zeros. So this increment value that I mentioned before is 11. So that means that I can increment my source pointer by 11 to get to the first octet in the next sequence that's not ASCII, and I can adjust my destination pointer, add 11 to it, so now I'm pointing at the next location in memory to which I will write more code points in the future. So I'm done converting, and at that point, I drop into the advance. I come back out of the loop. I know that my next octet is not ASCII, so I'm going to fall into advance, and then I'll walk through the state machine in the same way that I did when I showed you the basic algorithm. Okay, so that works pretty well. So I started thinking, can I make it even faster with AVX2 or AVX512? So now I'm going to write this function, convert ASCII with AVX. And this, for me, turned out to be one of those rare cases where I made the function inline, but I got better performance by actually putting the code itself inline where I would have called the function. So I'm effectively treating this like it's a macro. So I'm going to show you what that looks like. So here's my P source. All right, now I'm going to expand this macro. Here's P source, and here's the code. I've got the mask and the increment again. I've got my chunk register. I've got another register that I call half. But this register is an AVX2 register. It's twice as wide. So I'm going to load the same 16 bytes of data into chunk. So there's my memory location. I'm loading it into chunk. And now I'm going to zero extend in one instruction the lower 8 octets in chunk. And this instruction from the AVX2 intrinsics will do that in one shot. There's no need to unpack and interleave. You just do it in one shot. So I call that with the with chunk. It takes the lower 8 bytes and it unpacks them in one shot into half. And here, because I didn't have room on the screen, I've drawn half, which is 32 bytes wide in rows of 2. So this is the least significant byte, and this is the most significant byte. But if you look at the pattern here, you can see that they've been zero padded. Then I store that to memory. So I write that out. So I'm writing out, and here I'm drawing the whole buffer. So I'm writing out the first 8 octets. And at this point, I found that it was fastest to compute that mask, move mask at this point. So I do it. I compute the mask. And now I'm going to shuffle the bytes that are in chunk. I'm going to swap the lower 8 bytes with the upper 8 bytes. So there's a macro which creates a bit mask, which you can pass as intrinsic, which will do that shuffling. So here I've done the shuffling. You can see I've taken the upper 8 bytes and moved them down here, and the lower 8 bytes and moved them up here. I'm going to do the same zero extension that I did before into the half register, except now it's with the bytes that were originally in the upper half. And I'm going to store in the next locations. So I've written the same 18 or the same 16 code points to memory as I did before, but I've used fewer intrinsic instructions to do it. And the question is, will I get better performance if I'm not doing as much work with registers? Once again, I use the mask to get the trailing zero count, which is 11, and I adjust my input and my output pointers accordingly. And then I go back to the top of the loop. I know that it's not an ASCII byte next, and I drop into advanced to do the DFA-based computation. So how fast is this? Did I get any performance benefit? Well, let's look at some testing, and I actually end up just extending the testing that I did 2 years ago. I've improved the compilers, though. I actually did most of this work before I built GCC 10 for myself, so I did it with GCC 9.3. And these were all built on Ubuntu 18.04 on a Core i9, a machine that I own. And all the code was compiled -03 with the AVX2 intrinsics enabled. And curiously, and I'm not an expert at GCC flags, but the lowest architecture I could find in the GCC man page that supported machine type of AVX2 was Skylake. So I turned on Skylake. I also ran it on the same machine running Windows using Visual Studio, a very recent version of Visual Studio to do the compilation. So I mentioned before that I had gathered these input data files, and these are the same files that I used 2 years ago. I have a Wikipedia entry in English, a Wikipedia entry in Chinese, a Wikipedia entry about Hindi in Hindi, Portuguese in Portuguese, Russian in Russian, and so forth. I also have 3 stress tests, stress test 0, 1, and 2. The first stress test has 100,000 ASCII code points in it. That's all. It's effectively a no stress test because there are no multi-byte sequences in it. The second stress test is one where every sequence is a 3-byte sequence. So there's 100,000 Chinese code points from Chinese. There are 3 code units per code point, so there are 300,000 code units, 300 kilobytes. And finally, stress test 2, where I had 50,000 Chinese code points interleaved with 50,000 ASCII code points. So there would be a 3-point Chinese code, a 3-unit Chinese code point, followed by an ASCII code point, followed by the same thing repeating over and over again. And this is really a torture test. So I wanted to compare my conversion against other libraries. So I used icon from the GNU library, which I consider to be the gold standard because everybody seems to refer to it and it seems to get things right. I'm sure perhaps some UTF and internationalization experts would disagree with me, but seemed like a reasonable choice. There were UTF conversion functions that were part of the LLVM distribution that go into Clang. There was an implementation by a gentleman named Alexei Vichenko that converted UTF-8 to 32. I used std code convert from the standard library's UTF implementation, which will also do this, albeit very slowly. I used boost.txt, although this is the same version of boost.txt that I used 2 years ago. Zach Lane has recently greatly improved the performance of boost.txt, so don't pay much attention to that column in this presentation. Didn't have time to integrate his code and make it work. But because I used it previously, I decided to include it in this one. There's an alternative DFA implementation by a gentleman named Björn Herman, and this was part of my original presentation. And he actually derived, we derived the DFA independently, but he did it 10 years before I did. And I found it after I'd already done all the work and sort of hit myself in the head for wasting so much time. So the timings are what you might expect. I read the input file, I create the output buffer, I start a timer, I enter a loop. I perform the conversion on the buffer multiple times. And the idea is the number of repetitions, regardless of the size of the buffer, should be about 1 gigabyte of input text. That's what I was going for. Exit the timing loop, stop the timer, collect and collate the results. To pass, every library had to agree with icon, and in fact, they did. So let's look at some timings. Here I've got the timings for GCC 9.3 on Ubuntu 18.04. And along the bottom here are the color codings. You've got ICOM, LLVM, Alexei Vichenko's, std code convert. You've got boost.txt. You've got Björn Herman's implementation. And then you've got my4, the basic ASCII, the improved ASCII, the ASCII improved with SSE, and the ASCII improved with AVX2. So you can see in the case of English, where it was all ASCII code points, it was quite a bit faster. It was probably, it ran in about 62% of the time of the SSE-based solution. However, when you start getting to large multi-byte sequences on GCC, the performance delta goes very close. The delta is almost 0. And here for Chinese and Hindi, there was effectively no difference in performance. And in fact, with Hindi, the AVX2 implementation was a little bit worse. If we look at Portuguese, Russian, and Swedish, Portuguese and Swedish have a lot of 2-byte sequences. Russian has a lot of 3-byte sequences in it. So for the 2-byte sequences, we see a little bit of improvement with Portuguese and Swedish. We see worse performance actually with Russian with the 3-byte sequences. For our torture tests, I think this is very interesting for the torture test. The performance with the SSE and AVX for 100,000 ASCII bytes was exactly identical. It never differed on GCC. However, when it came to stress test 1, which is all Chinese code points, both the SSE and the AVX-based approaches were faster than the improved ASCII approach, but they were still not as fast as the basic approach. Remember, the basic approach just went into the DFA every time. It was not doing that extra branch to check for ASCII. So in the case where there was no ASCII, it was always fastest. But AVX was actually worse than SSE. And then on the case of the interleave Chinese and ASCII code points, there was effectively no difference between the AVX and SSE implementations. So this was the behavior on GCC. And it's very strange, I think, relative to the behavior that I observed with Clang and with Microsoft's compiler. Now, here are the same graphs, same data, same machine, run on the same day. And here, the performance improvement when going to the AVX-based implementation is actually significant for all languages. In fact, you can see here for the English wiki that the AVX-based approach on Clang is almost exactly as fast as the AVX-based approach with GCC. But the important thing is that if you're using Clang, there is a performance benefit here. We see it for English, for 3-byte units, for Chinese, 3-byte sequences for Chinese and Hindi. We see a big speed up for Portuguese. We see a big speed up for Swedish with their 2-byte sequences. We still see a reasonable speed up for Russian with its 3-byte sequences. And we go to the torture tests. Well, of course, with the ASCII torture test, we do better. We do twice as fast. There is really no difference here at all between AVX and SSE with the fully Chinese and the Chinese ASCII interleave. I don't understand why I have this performance difference here for the improved basic approach. I have to go back and dig into that. That's the one inconsistency I found with compiling with Clang. I saw similar sorts of results, not quite as big of improvement, but with Visual Studio. So here, running on Visual Studio, I see about a 10% difference in everything. So about a 10% difference here for English, about 10% for Chinese, about 10% for Hindi. And again, for Portuguese, about 10%. Now for Russian, not as much for Russian. I don't understand that. Russian is a tough language to translate, or maybe it's just the Russian wiki page that I was using. And Swedish, curiously, there wasn't much difference in that either. When I looked at the torture tests, I did a little bit better with AVX versus SSE for the all ASCII. For all Chinese code points, again, I did quite a bit better, actually, more than 10%. And then for the alternating Chinese and ASCII code points, I did a little bit better. But the thing that I find interesting is that, first of all, that I'm happy that I saw these improvements in performance with Clang and Visual Studio. I'm a little bit curious about why I didn't see the performance improvements with GCC. If I look at the absolute timings, GCC tends to have the best absolute timings. So perhaps GCC has already figured out how to optimize the sequence of machine instructions in an optimal way, in a way that perhaps Clang and Visual Studio have not yet implemented, although I'm sure they probably will. So sort of mixed results. 2 out of 3 compilers I got reasonable, I would consider acceptable performance improvements for, especially if you use those compilers. For GCC, I would say there's effectively no difference and you'll get good performance either way. So that is the end of my presentation, the second half. There's my GitHub and my blog. These slides will be up on the blog today for today's talks. The code that you saw, I'm going to do a little bit of cleanup and commenting so it's decipherable. And the code will be up and included in the blog before you get to work Monday morning. So thank you everyone for coming. I've got 3 minutes left and I see some questions on Remo and I'm going to attempt to answer them. So the first question is there a drawback to have 16 registers used for kernel coefficients when the register count is limited? I don't think so. The change in performance from going from, I actually tried convolutions for just for the fun of it, for all values from 1 to 16. And the change in behavior it didn't seem to make a difference, even with the limited number of registers. And I suspect when the optimizer works its magic behind the scenes, it's not actually loading all of those things into an array. I suspect, well, I know that it's unrolling the main loop. And since it's unrolling the main loop, it may have looked at the initial loop where the kernel coefficients are stored and just simply written those things out to memory somewhere. And then in the unrolled loop, it just pulls those things out as it needs them from memory, loading them into a register, rather than keeping them always in a register. What is the impact of passing SIMD register values to function by value or reference and the impact of using lambdas? Well, I haven't tried any of this code using lambdas. It's intentionally designed to be very simple. In fact, I was really intending to use operator overloading to give me a consistent interface, a consistent forced inline interface, so that I could overload a single name function for ints and floats and doubles and chars. In terms of performance between passing a value, a register by value, and passing a register by reference, I'm able to detect no difference. I tried to use a form where the, registers are passed by value and you get a return. You use the return value, sort of a functional style. However, there was the one function, in place shift up with carry, where I used references because I didn't want to deal with returning a tuple and possible performance degradation from that. It was just easier to use references. Next question. Could you put the code on Compiler Explorer and see what the difference is between GCC and Clang? Yes, I absolutely could do that. And as I was developing it, I actually had hard-coded, instead of having the template when I was originally developing the code, I actually hard-coded the parameters into the function rather than making them template parameters. And once I got it working for a couple of different values, 5 and 11, I think, then I went back and turned it into a template and then checked it for 3 through 15 odd numbers. And while I was doing that, I was actually taking those and dropping them into Explorer to see what was being generated. But to be honest, I didn't try actually looking at the opcodes, the difference in the instructions between GCC and Clang. In my copious free time, that's something I hope to get to someday and see what the difference is. But even if there was a difference, I'm not enough of an assembler expert, and I don't know really enough of the deep details of how the Intel architecture works to look at the instructions and say, aha, here's the reason why this thing is slower than this other thing. Are you aware of SIMD implementations for mathematical special functions, Gaussian error function, for example, that are publicly available? No, I am not. It's not something I was looking for when I did this work. As I said, I was playing around with some signal processing on an audio signal, and it led me down this rabbit hole. And since I had had the experience 2 years ago with the SSE, I thought, hey, maybe I can use intrinsics to make this audio processing faster. That being said, I think taking the AVX-based approach and turning it into a publicly available library is a great idea and something I would like to either initiate or participate in, but I'm not aware of anything like that right now. How did I mix ASCII and Chinese characters in stress test 2? So basically what I did is I created a sequence of 100,000 code points. And remember, a code point is a 4-byte integer. And the code points in that array began with a Chinese character followed by an ASCII character code point. And that pattern followed. So there were 50,000 Chinese code points interleaved with 50,000 ASCII code points. Chinese, ASCII, Chinese, ASCII, Chinese, ASCII. So I had the code points in UTF-32. Then what I did is I just wrote a function to convert the UTF-32 code points back into a sequence of UTF-8 octets. And that's how I got the UTF-8 input for stress test 2. And of course, part of stress test 2 is taking the UTF-8 that I convert and comparing it to the original code points to make sure that they match, and they should, and they did. But that's how they were generated. So, all right, well, I see that I'm out of questions and I'm out of time. I ran 2 minutes over. Thank you, everyone, for coming to this talk. As I said, the slides will be up on GitHub tonight and the code this weekend. Thank you very much. Have a good rest of the conference and take care.